All right, so the following set of examples asks you to find the inverse of a one-to-one function. Now, just remember what a one-to-one function is. A one-to-one function is a function in which for each y value, there's exactly one x value. So remember, a function was the other way around. For each x value, there's exactly one y value. A one-to-one function is the other way around. For each y value, there's exactly one x value. And so that would make that function a one-to-one function. And it turns out that if you have a one-to-one function, then you can find its inverse. And that inverse will also be a function. All right, so you learned about that in a previous lesson. And what you want to do in these problems here is you want to find the inverse of a one-to-one function. Now, the fact that you're told that these are one-to-one functions, you can automatically find the inverse. So, for example, let's suppose we had, and this is going to be number 48. So, number 48a, you have this function. The function is f of x is equal to 7x minus 5. All right, so you have this function. Now, without me telling you that this is a one-to-one function, you could indicate or you should know that this function here is actually a one-to-one function. And how should you know that without me having to tell you it's a one-to-one function? Well, one way to do that is to graph this function. So let's go ahead and graph this, and notice that this is a linear function. So this function here is linear, 7x to the first power, see that first power, minus 5. So that's a linear function. So let's just go ahead real quick and graph this just to verify that that is a one-to-one function. So let's go ahead and take out a coordinate plane. Okay, so we're going to go ahead and graph this function. So let me go ahead and write, now remember, f of x, I'm going to go ahead and write this as y. So y equals 7x minus 5. Now remember, that's a linear function. And so I can graph a linear function or a line, right? This is a line. So I can graph a line by just using a t-table. And so let me just go ahead and use a t-table. I could also use the y-intercept and the slope, which I'll show you as well. But if I use a t-table and all I really need are 2 points, you may want to use 3 just to make sure that all those 3 points are collinear, they lie in the same line. But if x is 0, notice I get 7 times 0, which is 0, minus 5, which is negative 5, so there's one of my points. If x, let's say, is 1, I get 7 times 1, which is 7, and 7 minus 5 is 2. And so if I graph this line just using those 2 points, let's see, I'm going to get 0, negative 5, which is here, right here. And I'm going to get 1, 2, which is here. And then using a ruler, we have this. So let me go ahead and draw this line. All right, so we have this line here. And notice that this line that I've drawn is a one-to-one function. So remember, a one-to-one function, now first of all, remember a function, you know this is a function because it passes the vertical line test. Remember the vertical line test? So no matter where I draw that vertical line, it intersects it once everywhere. But for a one-to-one function, you know this is a one-to-one function because it passes the horizontal line test. No matter where I draw a horizontal line, it's going to intersect this line just once each time. So it passes the horizontal line test, so that's a one-to-one function. What you want to do, though, is find, now remember, you want to find the inverse. Remember the notation. So the notation would be f inverse, see that negative 1, so f inverse of x. Now be careful because that negative 1 does not mean an exponent. So don't say f to the negative 1 power. We just call it f inverse. And so that's what you're trying to find. All right. Now, going back to that definition that we had earlier, a function for each y value, there's exactly one x value for a one-to-one function. Notice that and I'm going to go ahead and use a few more points. If I let x be 2, let's say, 7 times 2 is 14. 14 minus 5 is 9. If x is, let's say, negative 1, I get 7 times negative 1 is a negative 7. A negative 7 and a negative 5 is a negative 12. And I can continue on. But the point is this. If I look at this in terms of a mapping going from y to x, all right, so remember for each y value, there's got to be one x value. So in y is negative 5, I have just one x value, and that is 0. So when y is negative 5, there won't be any other x values except 0. When y is 2, there won't be any other x values except when x is 1. So 2 gets mapped to 1, negative 5 gets mapped to 0, 9 gets mapped to 2, and so on. So notice that for each of those y values, there's exactly one x value. So that makes this function here a one-to-one function. And the fact that we have a one-to-one function, we can find the inverse. So we can find the inverse of this function, and we're going to do this algebraically. So you want to do this algebraically. All right, so let's remember the steps. So step 1 is to replace f of x with y. So we have y equals 7x minus 5. Now remember when we talked about inverse functions, so remember when we talked about inverse functions, when we compared f of x with the inverse, the x's became the y's and the y's became the x's. All right, so remember when you're looking at the inverses, the coordinates are interchanged. All right, so for example, see this coordinate right here? With that, well, we had 1, 2 right here, that coordinate. So 1, 2 is on the graph of f of x. If you interchange the coordinates 2, 1, that's going to be on the graph of the inverse. So 2, 1. So 2, 1 will be here. So when you look at this point 2, 1, that's going to be the inverse. So the x becomes y and the y becomes x. So that's one of the lessons that you learned when you looked at the section on inverse functions. And so that's one of the properties of inverse functions. So if xy is on the graph of x, then yx will be on the graph of the inverse. All right, and we're going to come back to this in a little while just to remind you some other ideas, some other properties that you learned. But going back to the idea of that slope in the y-intercept, so you see the y-intercept's negative 5, right? So that's where the graph's going to cross the y-axis. And so since this is a linear function, you can use the idea of slope and intercept. So the intercept is negative 5, the y-intercept, which you see it here. And the slope is, in this case, I'm just go ahead and write it. The slope is 7, which I can write as 7 divided by 1. So from this y-intercept, I'm going to go up 7 units. Remember, rise over run, so positive, positive right here. So I'm going to go up 7 units, 1, 2, 3, 4, 5, 6, 7, and then to the right 1, and there's the point we found. Remember that point 1, 2, and then you just draw your line. All right. Okay, now let's go back to this. So the first step you had to do was to replace f of x with y. Then you interchange the coordinates. So that goes back to what we talked about here. So 1, 2 becomes 2, 1 on the inverse. So you interchange the coordinates. So in other words, y becomes x and x becomes y. That was your next step. And then all you do is solve for y. So the next step is to solve for y. So to do that, I'm going to add 5 to both sides. So let me go ahead and write this out right here. Solve for y. That will be your next step. Solve for y. So remember, you replace f of x with y, then interchange the coordinates. So interchange the coordinates. All right. And then you solve for y. So I'm going to add 5 to both sides. And when I add 5 to both sides, I get x plus 5 is going to equal 7y. And then to get y by itself, I'm going to go ahead and rewrite this over. To get y by itself, you can divide both sides by 7. And simplifying this, you get y equals x plus 5 divided by 7. Now, this y right here, all right, this y. Remember, this y right here was the f inverse, right? So I'm sorry, it was f of x, right? So we interchange the coordinates. So now this y now becomes f inverse. So you're going to say now that equals f inverse of x, and there's your inverse. So f inverse of x is going to equal x plus 5 divided by 7. So that all goes back to the interchange of the coordinates. So f of x, y, we interchange the coordinates, so now y becomes f inverse. Okay, when you solve for y, that becomes f inverse. All right, and so this right here, if you were to graph the inverse, see this is the graph of f of x. If you were to graph the inverse, and remember f of x here is 7x minus 5. So if you were to graph the inverse, this would be the equation of that line. All right. Now let's just kind of remind ourselves about something here. So remember, inverses are symmetrical. Let me go ahead and write this out right here so you can remember. So this is kind of review as well. So inverse functions are symmetrical about the line y equal x. All right, so inverse functions are symmetrical about the line y equals x. So in other words, if you were to draw, I'm going to use a different color here. If you were to draw this line y equals x, so remember y equals x means this, means that y and x are always the same value. So make sure you understand what that means. You learned that in that lesson, in those lessons. So in other words, y is the same as x. So if x is 0, y is 0. If x is 1, y is 1. If x is negative 1, y is negative 1. That's what that means. Okay? If y is 2, x is 2. Y is negative 2, or if x is negative 2, y is negative 2 as well. So notice x and y are equal to each other each time. So if you graph this line of symmetry, or the symmetrical about the line y equal x, you're going to get 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 1, negative 2. So you see these little points here I'm drawing in orange. And if you were to graph this line here, now remember that's the line y equals x. So I'm going to put it as a dotted line for right now. All right, so there's the line y equals x right here. All right, so you learned that in one of the lessons. So there's the line y equals x. So what that means is that this function right here, f of x, the inverse, when you graph the inverse, those two lines are going to be symmetrical about this line y equals x. Now remember, 1, 2 becomes 2, 1, right? And you see this 0, negative 5 right here? So let's talk about that. 0, negative 5. So 0, negative 5 becomes negative 5, 0. And negative 5, 0 is right here. Okay? There's negative 5, 0. And so when I draw, and let me see if I can get a different color here. And so when I can't find a different color, so I'm going to use the black pen again. But when I draw the line here, I want you to notice something right here. I'm going to draw this line right here. And let me make sure that the ruler goes over those 2 points, just like this. And right here, this line I've just drawn. So you see how this part, when I reflected about the line y equals x, I get this line right here, or this part. And then when I take this piece right here and I reflect it, see there's a line y equals x, and I reflect it about the line y equals x, I get that piece here. So this function f of x and the function f inverse are symmetrical about that line. Now what you found here, the equation of that line, is actually this right here. This right here. So x plus 5 divided by 7. So f inverse of x equals x plus 5 divided by 7. So that right here is the equation of this line. All right, so that's one of the some of the ideas that you learned when you went over those lessons on inverses. All right, but for our for our problem here though, where they ask you just to find the inverse, you're going to find the inverse algebraically and you do these steps. So the steps would be replace f of x with y, interchange the coordinates, solve for y, and that becomes your inverse. So you have to say f inverse of x, so you have to write it like this, f inverse of x equals this expression right here. All right, so that's part A. So let's look at part B. So 48b. So in 48b, you have this function. So 48b, you have g of x is equal to 3x squared minus 5. Now, we have to be a little bit careful with this. So notice that this is a quadratic function right here. And remember, if I just draw a quadratic function, and since there's no x term, that means that when x is 0, your y-intercept. When x is 0, my y-intercept's negative 5. So it looks something like this right here. And remember, this right here that I've drawn, this is, right here, that function is not one-to-one. Not, oops, this is not a one-to-one function. Okay? That's not a one-to-one function because it fails the horizontal line test. It fails the horizontal line test. Notice that when whatever this y value is, there are going to be two different x values. Same thing here. If I look at this y value, there are going to be two different x values. Look at this y value, there are two different x values. So that is not a one-to-one function. But you may say, but you said that each of those functions are one-to-one. All right, so one thing you learned was this. We have to restrict this. In other words, if I just look at this piece right here, so if I restrict the domain and only look at this piece right here and forget about this piece, then this will be one-to-one. So one of the things you learned was that in particular, if you had a quadratic function, because you know that quadratic functions are not one-to-one functions, but if you restrict part of it, if you restrict part of the domain, don't look at the other part, then that restricted domain is going to be a one-to-one function. And so that's what you see here. So you're going to see something like this. You're going to see for, in this case, will be x greater than 0. So if I restrict the domain strictly from x equals 0, which is what you see here, then this part is a one-to-one function. Okay? All right, so that's why you're going to see this right here. So this is a one-to-one function because the domain is restricted. All right, now I didn't have to do that here. See, I didn't have to restrict the domain here because that line we drew was already a one-to-one function. So if you remember right here, that line we drew was already a one-to-one function. No matter where I drew that horizontal line, it would go through the graph just once. So that was a one-to-one function. But this right here, when I drew that quadratic function, it was not a one-to-one function. So that's why we have to restrict the domain. All right, and so you just do it the same way though. So you're going to say replace g of x with y. So we have y equals 3x squared minus 5. Then we interchange the coordinates. So y becomes x and x becomes y, just like this. Okay? And then we got to solve for y though. So let's go ahead and solve for y. So to solve for y, we're going to first of all add 5 to both sides, just like this. And so I get x plus 5 is equal to 3y squared. Then remember, got to get y squared by itself, so I'm going to divide both sides by 3. The opposite of multiplication is division. And so I have this so far. So I have x plus 5 divided by 3 equal y squared. Now remember, this time we're trying to get we're trying to get y by itself. So right now I'm squaring y. The opposite of squaring is to take the square root. Okay, now you got to remember something. So remember in the past when you solved a quadratic equation and you took the square root of both sides, you did that plus or minus. You don't do that here. All right, you don't do that here. So when you take the square root of both sides, you're just going to take the positive square root. All right, so this becomes y equals the square root of x plus 5 divided by 3. And that is your inverse. All right, so that's going to be your inverse. All right, and so you're going to say f inverse of x is going to equal the square root of x plus 5 divided by 3. Okay? And so that's how you do. That's how you find the inverse. Don't forget though, don't do that plus or minus. All right? Um, don't do the plus or minus. It's just going to be the square root of x plus 5 divided by 3. Okay? All right, so if you do that plus or minus, you're going back and not remembering that this domain was restricted. All right, so remember we restricted the domain. All right, so we have to be careful then. Since I restricted the domain, I've got to be careful and not use that plus or minus anymore. All right, so that was part B. So let's go to part C. All right, and so in C, we have this for C. We have h of x is equal to x plus 1 divided by 2x minus 3. All right, so I have this rational function. So remember, that's a rational function. Okay, and this rational function is a one-to-one function. And so we're gonna go ahead and find the inverse. All right, now be careful with a rational function because notice there x is in the numerator and an x in the denominator. So you have a little bit of work to do compared to a linear function, which is always the easiest. A linear function to find the inverse, that's always the easiest to do. You have a quadratic, which is not that bad. You just have to remember, don't do that plus or minus. It's just a positive square root you're going to end up with. And then this one is a little bit more challenging, but you know enough algebra to be able to do this. Okay, so step one, remember is to replace h of x, replace h of x with y. So I have y equal x plus 1 divided by 2x minus 3. Then remember the next step is to interchange the coordinates. So y becomes x and these x's become y's. So x equal y plus 1 divided by 2y minus 3. All right, so that's your next step. So you have to show each of those steps. Now we have a rational equation here. And so I'm going to go ahead and rewrite x as x divided by 1. And notice this is a proportion. So I have a rational expression equal to another rational expression. So I can just go ahead and cross multiply if I want to. Or if you look at this, the LCD is 2y minus 3. So one of the things you learned when solving irrational equations is that you have to find the least common denominator. So the least common denominator is 2y minus 3. And then once I find the least common denominator, I'm just rewriting this part over. Once I find the least common denominator, then I can multiply both sides by that least common denominator. All right, and so let's go ahead and do that. Now remember, cross multiplying gives you that same thing here. So we have x times 2y minus 3. So I'm going to write it as x times 2y minus 3, just like this, equal. Now on this side, notice that the factors 2y minus 3 divide out, so you're left with y plus 1. All right, so that's where we're at. Now remember, at some point you have to solve for y. Okay, so you have to solve for y. Notice though that you have y's on both sides of the equation. So what we're going to do next now is we're going to distribute the x, and we can get rid of that parentheses. I'm using a distributive property. So I get 2xy minus 3x, so I multiply both of those by x, equal y plus 1. And now we're going to bring all the terms that have y on one side and everything else to the other. So see, this term right here has the factor y. So I'm going to bring this one over. So I'm going to subtract y from both sides. And so what I have then is 2xy minus y minus 3x. So I have three terms here. You see that? equal y minus y is 0, 1. Then we're going to add 3x to both sides, just like this. And so I get 2xy minus y, this is 0 here, is equal to 3x plus 1. Okay, so that's where I'm at. Now, remember, I want to solve for y. So if you look at those two terms here have a factor of y. So that's my greatest common factor. So I can factor out a y now. So I'm going to go ahead and factor out a y. So I get y times 2x minus 1. Remember, y times 2x is 2xy. Y times negative 1 is negative y. Equal 3x plus 1. And then to get y by itself, right now I am multiplying 2x minus 1 by y. So the opposite to get y by itself is to divide by 2x minus 1. So I'm going to go ahead and just rewrite this over. And then I'm going to divide both sides by 2x minus 1. And then notice when I reduce, I get y by itself. So y equals 3x plus 1 divided by 2x minus 1, and that is your inverse. And so therefore you're going to say f inverse of x will equal 3x plus 1 divided by 2x minus 1. And that's the inverse. Okay? So here's your function. Oops, I'm sorry. That's h of x, right? So this, be careful. This is, don't say f inverse. You got to say, that was my mistake. You have to say h inverse of x. So h inverse of x equals this. All right, so that was my mistake here. H inverse of x is 3x plus 1 divided by 2x minus 1. All right, so be careful. And I think I may have made the same mistake on this one as well. So remember, this is g of x, right? So the inverse is going to be called g inverse of x. So right here, this has to be a g. So don't forget to make that a g. Okay, g inverse. Same thing here. G inverse. Okay? All right, so just be careful with the notation. I wasn't very careful here. So just be careful with the notation. This is g of x. You have to say g inverse of x. Okay? If this is f of x, you have to say f inverse of x. If this is, let's say, in this case it was what? H of x, you then have to say h inverse of x. Okay? All right, so be careful with the notation so you don't lose any points. All right, so that was that part of the direction. So that part of the directions just asks you to find the inverse of each one-to-one function, and you're going to find it algebraically. All right, so that was number 48. Okay, number 48. All right, now real quickly, number 49, just to look at those problems. So here's number 49. So 49 asks you the following. It says, determine if the following functions, all right, the following functions is a one-to-one function. Okay, so determine if the following functions is a one-to-one function. So remember we talked about earlier, so if a function is one-to-one, so remember one-to-one, if we go back to our example here, a function is one-to-one if for each y value there's exactly one x value. All right, and so if you have one y value, so for each y value there's exactly one y value, then it is a one-to-one function. All right, and so remember one of the ideas that we were using in some of our examples was the horizontal line test. Horizontal line test. That's what we use to determine or to see that a function was one-to-one, which implied it also has an inverse. All right, the horizontal line test. So what you have to do here, so if you look at part A, you have f of x is equal to 3x minus 1. So the best way to do these problems here when determining if the following function is a one-to-one function is to think of its graph. That's the best way. And so think of the graph. And so if I look at f of x equals 3x minus 1, and you just have to do this in your mind, right? You don't have to use a coordinate plane. You know this is a line. That's a line, right? And so if I look at this line right here, and I think about the slope and the y-intercept, the slope is 3 and the y-intercept b is -1. So if this right here is the y-intercept, -1, and if the slope is 3, I go up 3, 1, 2, 3, and then to the right 1, I have this line right here. So this is f of x. And notice that this line passes the horizontal line test. So it passes the horizontal line test. And so since it passes the horizontal line test, then we're going to say f of x is a 1 to 1 function. All right, so it's a 1 to 1 function. Okay, let's look at b. In b, we have h of x is equal to x squared plus 4. All right, now remember, there's no restriction, just like you saw in the other problem that we did earlier. You're just told this. So now you got to look at the graph of this. So remember, x squared looks like this. I'm just want to kind of review something with you. So this is x squared here. See, it looks like this, where the vertex is at the origin. See that plus 4? Remember that plus 4, all that does is it shifts the graph of x squared up 4 units. So 1, 2, 3, 4. So you'll have this instead. Okay, look like this. All right, so that's the idea there. So if you look at the graph of h of x, then it'll look something like this. But in particular, oops, that's h of x, so be careful with your notation. In particular, though, notice that this function here, this function fails the horizontal line test. Notice that when y, whatever this y value is, there are going to be 2 different x values. So remember the definition of one-to-one function, for each y value, that can only be one x value. So h of x, which is this function here, fails the horizontal line test. So we're going to say then, we're going to say h of x is not a 1-to-1 function. And so as you do these problems, you have enough knowledge to do these problems just by thinking about its graph. Same thing for c. So if you look at c, you have k of x, which is the absolute value of x plus 2. Now remember we talked about this in the past, that an absolute value function has the shape of that v. Remember the shape of a v. A quadratic function, its graph is the shape of a parabola. The absolute value function is the shape of a v, where you have 2 rays that intersect at a same point. So you have this vertex here. All right, so that's the shape of that's a graph, or the graph of an absolute value function. So in this case, though, remember, let's just kind of review something here. So this is y equals f of x. All right, so remember, when I graph y equals f of x, so when x is 0, y is 0. When x is 1, y is 1. When x is -1, the absolute value of -1 is 1. All right, so we get something like this. And so we get this right here. Right away, you can see that an absolute value function is not a 1-to-1 function, right? So it fails a horizontal line test. So if this fails a horizontal line test, then what do you think about this, where we had x, the absolute value of x plus 2? Well, that should fail it also. Now, the graph of the absolute value of x plus 2 is this, right here. So, and you could use a t-table. So if x is -2, -2 plus 2 is 0. The absolute value of 0 is 0. So we get -2, 0 here. If x is -1, we have -1 plus 2 is 1. The absolute value of 1 is 1. So -1, 1 right here. If x is -3, we have -3 plus 1, which is a -1. And the absolute value of -1 is a +1. And so you see you get this graph here. All right, so this right here is the graph of the absolute value of x plus 2. Notice it fails the horizontal line test. So any variation or any translation or transformation of the absolute value function those will not be one-to-one functions either. All right, so it fails the horizontal line test. So for each of those y values right here, there are going to be two different x values each time, except for the vertex. But remember, it's got to pass the horizontal line test, which means that the horizontal line's got to intersect it once everywhere. So notice that there's an infinite number of places where the horizontal line test fails. All right, now notice that I got this graph here by using a t-table, but I want you to notice something. See this vertex here, 0, 0, right here? And when I graph this, that vertex is negative 2, 0. So to graph x, the absolute value of x plus 2, all I did was I took the parent function, notice I'm using the word parent function. I took the parent function, which is the main function, absolute value of x, and I shifted it to the left 2 units. All these points here were shifted to the left 2 units. And so notice that's the graph that you see here. All right. Now many students though will attempt to graph these by using a t-table, but you can also graph these by thinking about transformations. And so that's basically where you take a parent function and then you look to see what's happening to think about whether you move up, down, right, left. Okay? All right, so going back to here, so the horizontal line test fails, and so therefore k of x is not a one-to-one function. Okay. Now let's look at the last one. So the last one is D. And when I look at D, we have this. Let's see. So here's D. We have f of x is equal to the square root of x minus 5. Now that's a square root function. Okay, so remember, if you think about your calculator, you can only take the square root of 0 or a positive number. You cannot take the square root of a negative number. So if you took your calculator and you tried taking the square root of a negative 4, that's not a real number. You'll, if you, let me see if I can find my calculator. So if you take your calculator and you actually take the square root of a negative number, so I'll just kind of show you. So if you take the square root of a negative number, like this, and then say negative 4, notice you'll say domain error. All right, so you can't take the square root of a negative number and get a real number. So that's not a real number. Now, you learned something in the past. You learned that the square root of a negative 4, you can think of those in terms of imaginary numbers, right? So that would be 2i here. Remember, 2i is not a real number. That's an imaginary number. All right, so when graphing, and remember when we graph these functions, we always use real numbers, not imaginary numbers. All right, so when graphing this, I want you to know something. Use a t-table. So I've got to pick some values for x. So remember, the domain here, of the square root of x. So you got to think about this expression here, which is x. I can only take the square root of 0 or a positive number. So when looking at the domain, you got to think about the domain. When finding the domain, you take your radicand, which is x here, and you're going to say greater than or equal to 0, and you solve for x. Well, x is already by itself. So that's my domain. So meaning that when I go here and I pick some values for x, I've got to make sure that the values for x I choose have to be 0 or greater than 0. Okay? So I'm going to use 0. 0 is going to be the smallest one. So when x is 0, I have the square root of 0 minus 5. Well, the square root of 0 is 0. 0 minus 5 is a negative 5. So that's negative 5 right here. If x is, let's say, 1, see 1's in here, right? 1's greater than or equal to 0. I have the square root of 1 minus 5. Well, the square root of 1 is 1. 1 minus 5 is a negative 4. And when x is, let's say, 2, I get, I'm going to have to put that here. I get the square root of 2 minus 5. Now, you got to be a little bit careful here because 2 is not a perfect square. So that's going to be an irrational number. So let's just kind of estimate this now. So I have the square root of 2, square root of 2, and then minus 5. And that's approximately equal to negative 3 point, negative 3.6. Okay? Negative 3.6. And so I guess something like negative 3.6. I'm going to go ahead and choose perfect squares here. So if x is 4, I get the square root of 4 minus 5. Square root of 4 is 2. 2 minus 5 is a negative 3. Okay. If x is, let's say, 9, because 9 is a perfect square, I get the square root of 9 minus 5. The square root of 9 is 3. 3 minus 5 is a negative 2. All right, and so just real quick, just to show you, and let me just kind of, well, I can do it here. So here I'm going to go ahead and graph f of x, which equals the square root of x rather, square root of x minus 5. So when I plot those points that you see here, here's 0, negative 5, right here. All right, 1, negative 4, right here. 2, negative 3.6, so that's about right here. 4, negative 3, so that's about right here. Okay. And then 9, negative 2, that's about right here. So when I grab this, now notice it's a curve now. So it looks something like this. Okay, there's the graph. That's a graph of a square root function. So that is f of x, which equals square root of x minus 5. And then knowing the graph, notice that it passes the it passes the horizontal line test. So this passes the horizontal line test. And so since it passes the horizontal line test, we can say, so it passes the horizontal line test. So since it passes the horizontal line test, we can say that f of x is a one-to-one function. Okay, and also you could have right away determined that by noticing this right here. When for each of those y values, there's only one x value, and y is negative 5, my only x value is 0. When y is negative 4, my only x value is 1. When y is negative 3.6, my only, or approximately equal to negative 3.6, because that was an estimation, my y value is 2. When y is negative 3, my x value is 4. When y is negative 2, my x value is 9. So notice that for each of those y values, there's exactly one x value. So from there, I could have said right here, f of x is a one-to-one function. I did not have to graph this, although graphing it kind of helps you in somewhat to see what the graph looks like, but I didn't have to graph this. Okay? All right, so that is, those are problems numbers 48 and, let me go ahead and get problem 48 up here. So that was problems number 48 and 49.